Hello everyone, and welcome back to Mitchell's Physics Review. Today we are working on wire magnetic fields. Let's take a look at our problem. Two long parallel wires carry currents of I1, which is equal to 3.25 amps, and I2, which is equal to 5.25 amps, in the directions indicated in the figure below, where D is equal to 19 centimeters, and take the positive x direction to be to the right. First, let's just list all our givens. I1 is equal to 3.25 amps, I2 is 5.25 amps, and D is 19 centimeters or 0.19 meters. And let's also remember that positive x direction is to the right. Now that we have listed our givens, let's take a look at part A. Find the magnitude and direction of the magnetic field at a point midway between the wires. So let's draw a simplified form of our picture where we have X as the midpoint and our two wires, I1 and I2. So from here, we're going to draw a magnetic field vector diagram. Our diagram is going to show that B1 from this wire will be pointing upwards and B2 from this wire will be pointing downwards. Now, how was I able to determine which way the magnetic field would be pointing? Well, we're looking at the right-hand rule. So, for example, let's take I1. If there's this little dot, we know that our thumb should be pointing outwards because that is the direction of the current. Then we're going to curl our fingers around almost like we're wrapping them around a wire, and our fingers should be pointing upwards after we fully curl them. And then for B2, we're going to do the same thing, and after we fully curl them, it's going to look like they're curled downwards. So B2's magnetic field is going to be downwards. So that is how I got our vector magnetic field diagram with B1 pointing upwards and B2 pointing downwards. And now we can move on to the numerical portion. So we have B is equal to mu naught times I over 2 pi r. So we're going to be using this equation and solving for the magnitude in the middle. So we know that net B, or the net magnetic fields at that point, is going to be B1 because we call up our positive direction minus B2. So let's write our equations for B1 and B2. We're going to use this same equation up here, and this time plug in the current for I1, and we're going to plug in the radius for R1, and we're going to do the same thing with B2. Now we can rewrite them into our net B equation, and you're going to notice something as you're writing them, or from our picture. Since X is directly in the middle of both of the wires, R1 is going to be equal to R2. So we can just call them a general term of R instead of adding the subscripts. So we're going to get mu naught of current 1 over 2 pi r minus mu naught of current 2 over 2 pi r. From there, we can pull out the mu naught over 2 pi r, and we're left with mu naught over 2 pi r is multiplied by the quantity of I1 minus I2. Then we can use all of our givens. So we're going to plug in I1, we're going to plug in I2. We're going to use half of the distance from 0.19 meters, and we're going to use the constant mu naught. After we plug them all in, we're going to get that net B is equal to negative 4.21 times 10 to the negative 6 teslas, or negative 4.21 microteslas. But remember, we're just looking at the magnitude, so we're not going to leave this sign in our answer. So we're going to have 4.21 microteslas towards the bottom of the page, which is basically what this negative is telling us. But for our answer, remember, magnitude does not need signs. Now, let's look at part 2, which is determining the direction, keep this in mind, counterclockwise from the positive x-axis. So the easiest way I like to do this is drawing the x-axis, and then since we know this is towards the bottom of the page from our negative sign, I'm going to draw an arrow straight down representing that 4.21 microteslas. Then I'm going to start at the x-axis and draw a little circle around. The easiest way to do this is to determine from here to here is about 3/4 of a circle, or 270 degrees. And obviously we're going in the counterclockwise direction for that. So our answer for part 2 will be 270 degrees counterclockwise from the positive x-axis. Now, let's take a look at part B. Find the magnitude and direction of the magnetic field at point P, located D equals 19 centimeters above the wire carrying the 5.25 amp current. So first, we're going to be looking for the magnitude, and I really hope you enjoyed trig. So we're going to redraw the figure once again because it's easiest to visualize if we have the picture in front of us. And we're going to start by drawing our vector diagrams. Now this will be easiest if we start with B2, because using our right hand rule, we can find that B2 is just pointing directly to the left or on the negative x-axis. And B1 is a little more complicated because it's at an angle, so it's going to be shooting off. But through circles and radiuses we can draw, we'll find that this angle is 45 degrees, so I can save you a little trouble. Even if you eyeball it, it looks pretty close to 45 degrees. So we're going to have B2 going straight towards the left, and B1 going up and towards the left. So we can also break B1 now into its components, which the vertical component is going to be B1 sine 45 degrees, and the horizontal component is B1 cosine of 45 degrees. Now, similar to what we would do with forces, let's just break these up into x's and y's to make everything a little easier. Obviously, if we start with the y first, it'll be easiest because we only have one vertical component of the magnetic field. So we can say our first or only vertical component pointing upwards is B1 sine 45 degrees, and we can replace B1 with the equation mu naught I over 2 pi r, and then substituting in the specific current in radius for B1, which is I1 and R1, and then multiply that by sine of 45 degrees. We're going to do the same thing with the x's now. We're going to take B2, which is straight to the left, and we're going to replace it with the same equation and then substitute in the specific current and radius, so I2 and R2. And then finally, for the horizontal component of B1, we're pointing to the left, we're going to say B1 cosine of 45 degrees, replace B1, substitute in I1 and R1, then multiply by the cosine of 45 degrees. Now, we can keep simplifying. As you notice, we have R1, R2, and R1, and if you are fond of trig, you know that we have 45, 45, 90 triangle, meaning we can replace these radiuses. So with a 45, 45 triangle, we can know that two sides will be D, the two legs, and the hypotenuse will be D root 2. So in this case, R1 is going to be equal to D root 2, well, R2 will just be D. So now we can replace all of the R1s and R2s with D, which thus eliminates some of the more variables we had there. Then, after we rewrite our equations, now simplified with the R, we can start plugging in our givens. So let's start with the x's. For our first x equation, we're going to plug in the constant from U naught, the given current for I2, and put it over 2 pi, just the distance, which is 0.19 meters. And we're going to get 5.526 times 10 to the negative 6 Teslas. And then we can do that with the second equation. Once again, plugging in for the constant, the given current of I1, which is 3.25, and then over 2 pi, the distance, 0.19 meters, times root 2, multiplied by the cosine of 45 degrees, and get 1.711 times 10 to the negative 6. And then for the y equation, we're going to do that process another time, and we're going to plug in for the constant, plug in for the current of I1, put it over 2 pi times the distance of 0.19 times root 2, then multiply by sine of 45 degrees, and we get 1.711 times 10 to the negative 6. So finally, down here, we can just draw our triangle, which is a common theme in this problem, triangles. We have our upwards or vertical component pointing upwards at 1.5 microteslas, and if we add these two together, we have that it is pointing towards the left 7.23 microteslas. So here now is our simplified vector diagram for the magnetic field, and we have this as theta. So through Pythagorean theorem, we have B net is equal to the root of b squared of x plus b squared of y. And if we plug in our x and we plug in our y, we get that equals to 7.38 microteslas. Once again, B net is also the resultant vector, or this hypotenuse right there. So that's why we're using the Pythagorean theorem to solve for that. Then we are also looking for the direction in the counterclockwise from the positive x-axis. So now that we have this little vector diagram set up, it makes it a lot easier for us. So we know that theta will be equal to the inverse tangent of the opposite over the adjacent. So we can just say the theta is equal to inverse tan of bx over by. We plug in both of our values, and we get theta is equal to 78.28 degrees. Now, remember, though, we are starting going upwards. So 0.15. So if we draw it on the diagram, we're going to be going up, and here will be our vectors, this side and this side. So we need to add 90 degrees to that 78.28 degrees to find the complete direction counterclockwise from the x-axis, which as a result we get 168.3 degrees. So now that we have all our answers, let's take one last overview at this problem. For me personally, trigonometry is not my strong suit, so when tips and tricks like replacing R1 and R2 with D and D root 2, because we have a 45 and 45 90 degree triangle, was not as obvious to me, so I really struggled with some of the substitution and how to simplify my equations so that I could solve for them. But I hope this video helped you to learn a lot, as it did for me. Have a great day.